Hello everyone. Today we are going to talk about electric current in detail. Previously, we have explained capacitors and capacitance. So if you have watched that video, you will have a good foundation to understand what we are going to discuss now. To begin, let's consider a simple electrical circuit that includes a capacitor connected to a battery. In this circuit, electrons move from the negative pole of the battery toward the positive pole, creating a flow of charge through the circuit. If we examine the wire closely, which contains these moving electrons, we notice that the wire itself is a conductor. Now imagine focusing on a single electron in this conductor. This electron moves from the negative pole toward the positive pole, but at the same time, the electric field in the wire points in the opposite direction, from the positive pole to the negative pole. This might seem counterintuitive at first, but it is important to understand that electrons move opposite to the direction of the electric field. If we zoom in further and represent the wire with a three-dimensional diagram, we can see two distinct regions where the movement of electrons is clearly from the negative side to the positive side, while the electric field points in the opposite direction. To analyze this more quantitatively, we consider a small cross-sectional area of the conductor with length delta x. Electrons pass through this area, and each electron carries a charge denoted by Q. The total charge that passes through this cross-sectional area is the sum of all individual charges, which we call capital Q. The amount of charge, delta Q, that flows through this area during a small time interval, delta T, defines the electric current in this section of the wire. Electrons move with an average velocity called the drift velocity, denoted as VI, which is equal to the distance delta x divided by the time delta t. Therefore, by dividing the charge delta q by the time interval delta t, we obtain the average current. In words, current I is equal to total charge q divided by time t. The SI unit of current is the ampere, and 1 ampere is defined as 1 coulomb of charge passing through a cross-section per second. Here we see a transparent cylindrical wire connected to a battery and a switch. Inside the wire, tiny electrons are moving. When the switch is closed, the battery creates an electric field inside the wire. This field pushes the electrons so that they drift together in one direction, opposite to the field. This organized movement of electrons is what we call electric current. Now, let's examine the same conductor again. If the total length of this part of the conductor is delta x, then delta x is equal to the velocity of the electrons multiplied by the time delta t. The total charge, delta q, can be expressed as the number of electrons, n, E multiplied by the charge of each electron, q multiplied by the cross-sectional area A, and multiplied by the length delta x. Since delta x is equal to velocity multiplied by time, we can substitute this into the equation. When we divide delta q by delta t, the time delta t cancels out, resulting in a formula for the average current. Current I is equal to number of electrons Ni, multiplied by charge q, multiplied by drift velocity Ve, multiplied by area A. Here, Ne is the number of electrons per unit volume. Q is the charge of each electron, Via is the drift velocity, and A is the cross-sectional area of the conductor, which is perpendicular to the electric field. This formula shows clearly how current depends on the microscopic properties of the material, the number of electrons, and how fast they move. Now, moving on to resistance. Today we will explore what resistance means and how it relates to current. Let's examine a small section of a conductor with length L and cross-sectional area A, through which an electric field passes. The electric field has the same direction as the current. The right side of the wire has lower electrical potential, while the left side has higher potential. To describe the flow of charge more precisely, we define current density J, which is the current divided by the cross-sectional area. Fundamentally, current density J equals the charge density multiplied by the electric field. The potential difference across this section equals the electric field multiplied by the length EL. Therefore, current density J is equal to charge density multiplied by potential difference divided by length. By rearranging, we can express the potential difference as length divided by charge density multiplied by area times the current. This clearly demonstrates that the potential difference across a conductor is proportional to the current flowing through it, which is the essence of resistance. In fact, this relationship is written as voltage V is equal to resistance R multiplied by current I. The SI unit of resistance is the ohm, and 1 ohm is defined as 1 volt per ampere. Resistance can also be expressed as length divided by area, multiplied by 1 over charge density. Next, in the first section, the charge density gives us the resistivity of the material. In this case, the resistance formula, which includes resistivity, is equal to resistance equals resistivity times length divided by area here. If we want to better understand how resistivity affects resistance, we first need to pay attention to the length/area ratio in the formula. For example, let's consider 3 different conductive wires. Their lengths are equal, but their widths and cross-sectional areas are different. The wires have areas A1, A2, and A3 respectively. If the electric field is directed to the right, while the electrons move to the left, we can examine the length-area ratios. These ratios decrease as we move from the bottom wire upward. As this ratio decreases, the resistance increases inversely. In other words, as the area gets smaller while the length remains the same, the resistance becomes higher. Moreover, if we expand the 1/charge density term in the resistivity formula, we see that it directly depends on the length. Similarly, as the length of a conductor increases, the charge density per unit area decreases, resistivity increases, and consequently, the resistance also increases. To give a real-life analogy, walking on a long and narrow path is more difficult than walking on a short and wide one. For electrons, it's the same. Passing through a long and thin conductor makes their movement harder, increasing the resistance. As a result, both the formulas and real-life analogies give us the same message. Thank you for watching.